So further, with the continuation from the video one, here you are going to discuss kinematic pairs according to the type of contact you are going to have. So you are going to distinguish a lower pair and higher pair based on the surface contact. In the lower pair, you can see there will be a surface area contact. If it is a higher pair, we can expect point or line contact. In the lower pair, here as you can see in the diagram, a rectangular shaft moving in the rectangular block. So it is fixed on the both the ends. So it has got a surface area where we can allow the shaft to rotate. So if it's higher pair, you can see the contact between the pairing elements takes place at a point or along a line. So here you can see a gear, a spur gear which has got a surface contact, a bigger gear and a smaller gear, and you can see cam which is connected to the shaft where the cutting tool or the pointer which is at the top surface. So when the cam rotates at the top, so it is going to actuate the valve whether to open and close so that it has to output the charge inside the cylinder. So here, this is what the higher pair and lower pair indicates. So this is very much needed when we want to identify the mobility of the structure. So when we want to calculate the mobility of the structure, whether it is constrained or unconstrained, to define we have to identify whether it's a lower pair or higher pair. So based on the constraint what it has got, we have got a closed and unclosed pair. In the closed pair, we can expect both are held together mechanically to get the required relative motion. All lower pairs are closed pairs. If it is unclosed pairs, elements are not held mechanically, held in contact by the action of external forces. Example, we can expect cam and spring loaded polar pair. So if it is completely constrained motion, if we are going to define, so in the completely constrained motion, here we can expect the motion to be in a definite one direction only, and we cannot expect motion in any other direction. Second one is the successfully or partially constrained motion. So here we can expect that the constrained motion is not completely by itself, but by some other means. So here the constrained motion is successful when compressive load is applied on the shaft on the footstep bearing. So here when we add the load on one direction, here we can expect the shaft to move in one direction. So here the shaft is able to move only in the vertical position. So and above the given space, it cannot get dislocated from the mean position. If it is incompletely constrained motion, means the motion between a pair can take place in more than one direction. So a circular shaft in a circular hole may have rotary and reciprocating motion, and both are independent of each other. Means if you want a rotary motion, it is possible. If you want a reciprocatory motion, it is possible. Like that, you'll be able to carry out the constraint motion. So we define a kinematic chain. So group of links either joined together or arranged in a manner that permits them to move relative to one another. It is called as a kinematic chain. So best example is what we can take is a 4-bar chain. So L is equal to 2p minus half 4 that we can consider. J is equal to 3 by 2 into L minus half 2 we can consider, where P is the number of wire pair, L is the number of links, J is the number of binary joints. So if you want to identify number of links, you can use 2p minus half 4. If you want number of binary joint, 3 by 2 minus half L into 2 you can take. By using these two equations, you'll be able to calculate. So L is equal to 2p minus half 4. If you take, if LHS is greater than RHS, if you consider, then it is considered as a lock chain or a tangent chain. So in this case, no relative motion is possible. So this we are going to define when you want to identify whether relative position is possible or not. So if LHS is equal to RHS, means there will be a constrained chain, means the motion is completely constrained, means when we constrain at one point, we can expect the motion at the other end. So if LHS is lesser than RHS, then unconstrained chain we can tell. LHS is lesser than RHS, we can define that unconstrained chain it is going to happen, means the relative motion is not completely constrained, we can see in the output what all we get. So if you take a numerical example, how to calculate the uh, links and the uh, pairs. So here, if you take a chain, there are three links. L is equal link 1, link 2, link 3 is there in the ABC triangular structure. So number of joints are also 3. So from equation, if you take number of links is equal to L is equal to 2p minus of 4, it is you are going to get 2, where LHS is greater than RHS, so therefore it's a log chain. So if you take number of higher pairs, if you take 3 by 2 into L minus of 2, if you take, so if you substitute L is equal to 3, then you are going to get 2.5. So LHS is greater than RHS. So we can define it as a log chain. So further, if you determine the nature of chains, here it's given a 4-bar link and a 5 link mechanisms, where it be able to define whether it's a constrained or unconstrained chain. Here you can see the number of links are 4, number of joints are 4, and J value also it is equal to 4. So here LHS is equal to RHS. It's a constrained kinematic chain. So in the link, where there's 5 links, if you take, here you can see that L is equal to 5, P is equal to 5, and J also is equal to 5. So here LHS is greater than RHS. It's an unconstrained chain we can define. So further, if you take based on the nature of chain, so L is equal to, if you take count the number of links, here it is 6. Number of binary joints, what we take is AB and D plus 2 ternary joints E and C. So here one ternary joint is there. One ternary joint is there. 3 minus of 1, that is equal to 2 binary joints. So therefore J is equal to 3 plus 2 into 2. So therefore it becomes 7. So LHS is equal to RHS. So here the given chain, it's a kinematic chain or it's a constraint chain.